Many different types of applications of Bernoulli's equation exist, and one important application is known as Torricelli's theorem. So let's suppose we have the following tank, and at the bottom of the tank we have a spigot. Now let's suppose we fill our tank with a fluid and we open our spigot. So at the moment that we open that spigot, our fluid begins to flow out of the spigot, and the velocity of the fluid coming out of the spigot is given by V1. Now let's suppose that the cross-sectional area of the spigot is given by A1, and the cross-sectional area of this tank at the top is given by A0, and the velocity of the fluid at the surface of the tank is given by V0. Now, using the equation of continuity, we can get the following result. The velocity of the fluid at the surface of the fluid, V0, is equal to the ratio of V1, the velocity at the spigot, multiplied by A1 divided by A0, where A1 is the cross-sectional area of the spigot and A0 is the cross-sectional area of our tank. Now, notice if the cross-sectional area of the tank is much larger than the cross-sectional area of our spigot, this fraction A1 divided by A0 becomes very small. In fact, we can assume that this fraction is so small that our velocity V0 is also very small, and we can approximate the velocity of the fluid at the surface of the fluid to be 0. Now, let's also assume that the height, so the vertical distance from the bottom of our tank, from the ground to the surface of the fluid, is given by y0. And the distance, the vertical distance from the tank, from the bottom of the tank to the spigot, is given by distance y1. So that means the change in distance between our spigot to the surface of the water is given by the difference between these two numbers, y0 minus y1. This will become important in just a moment. So let's apply Bernoulli's equation for this situation, and let's solve for velocity V1. So we want to find a formula, an equation for the velocity that is the velocity of the fluid that is coming out of our spigot when we unlock that spigot. So let's begin by writing down Bernoulli's equation, which states the following. So notice that P0 and P1 are exactly the same quantity. Why? Well, because both the surface of the fluid and this section here are exposed to the atmosphere. So that means P0 and P1 are simply our atmospheric pressure, which is the same value at this point and this point. So we can cross out P0 and P1. Now notice we assume our initial velocity at the surface of the fluid to be 0. So that means this entire term can be canceled out. So this term is canceled out, this term is canceled out, and this term is canceled out. And we're left with the following three terms. So let's take this term from the right side and bring it to the left side, and we get the following result. Now notice every single term has a density value. So that means we can cancel out the density values because the density of the fluid at the surface as well as at this point in the spigot are assumed to be constant. And notice on the left side of the equation we have a g on each term. So we can bring that g out and we get the following result. Our gravitational constant multiplied by the change in our vertical distance between the spigot and the surface of our fluid is equal to 1/2 multiplied by V1 squared, where V1 is what we're looking for. We're looking for the velocity of the fluid in that spigot. So let's actually rearrange our equation and solve for V1. So we bring the 1/2 over, we get V1 squared is equal to 2g times the change in y, which is simply this distance here. And we take the radical of both sides, and we're left with our equation that we were looking for. V1, our velocity of the fluid that is coming out of the spigot, is equal to the square root of 2 times g times our change in height between our spigot and the surface of the fluid. Now, this result is known as Torricelli's theorem. And notice what it states. It states the following. Liquid leaves the spigot with the same speed as a free-falling object would attain if it travels the same vertical distance of change in y, of y0 minus y1. So if we take any object and we let the object go, and the object travels this distance, the velocity that object would attain would be the same exact velocity of the fluid that is coming out of the spigot. And that makes sense because this entire equation was derived from the law of conservation of energy, from the work-energy principle. And so it makes sense that eventually we get a result that depends on the law of conservation of energy. Once again, this result is known as Torricelli's theorem, and it comes from Bernoulli's equation. So let's look at the following example in which we're going to apply Torricelli's theorem. Suppose a tank with a cross-sectional area of 1 meter squared contains a spigot at the bottom of the tank with a cross-sectional area of 0.01 meters squared. If the spigot is 10 meters above the surface of the tank, calculate the velocity of the water leaving the spigot. So our fluid in the tank is water. The distance, change in y, is 10 meters. And we basically want to use this equation to calculate the velocity, the speed of our fluid as it comes out of the spigot. So we simply take this equation, we plug in 9.8 meters squared for our g, and we plug in the change in y. Well, the change in y is simply 10 meters. So 2 times 9.8 times 10, take the radical of that, and we get 14 meters squared is the velocity of the fluid that is coming out of the spigot when the change in distance between the spigot and the surface of the water is 10 meters. Now, let's just make sure that our assumption before was correct. Remember, we assume that our initial or our velocity of the fluid at the surface is very close to zero. So we approximate that velocity to be zero. So let's make sure that the velocity at the surface of the tank given in this example is in fact very close to zero. So we use this equation, which we once again obtain from the equation of continuity. So we have the ratio of our cross-sectional area of the spigot to the cross-sectional area of our container. So 0.01 meters squared to 1 meter squared. So that's 0.01, and we multiply 0.01 by the velocity of the fluid in the spigot, 14 meters per second, and we get a velocity of 0.14 meters per second. So notice this quantity is much smaller than this quantity, and that's exactly why we can approximate this quantity to be close to zero, because the number is very close to zero and it's much smaller than the velocity of the fluid in the spigot. So we see that this assumption in fact is a very good assumption. Now, many other types of applications and results of Bernoulli's equation exist, and another result can be seen in the following diagram. Let's suppose we have a pipe, and the pipe at two ends has different cross-sectional areas. So let's suppose on this side at point 0, at point 0, our cross-sectional area is A0, and at this point our cross-sectional area is greater than the cross-sectional area in this section. Now, let's also suppose that the height from the ground, our reference point, to this section, and the height from our reference point to point 1 is the same exact height. So there is no change in height between these two portions of the pipe, and the fluid flows in the following horizontal-like manner. So let's find our equation that will help us get the velocities at both ends. So we begin with our Bernoulli equation, well, Bernoulli's equation as described in this section. Now notice that our change in y is 0. In other words, y0 and y1, these two quantities are exactly identical. So that means we can simply cross these values out and we get the following result. So this is another important result that can be obtained from Bernoulli's equation that can help us find the velocity of the fluid within a certain pipe that has the following setup.